Hi, welcome here everybody. This is day number 10 and today's episode is brought to you by the letter W, which stands for work, and also it stands for watts. And today's class is going to be a bit of a life-changing moment, because after today's class you'll never look at another 60 watt light bulb again the same way as long as you live, because you'll know exactly what that 60 watts means. Just before we get into what we really want to do today, thanks for handing in all your tests yesterday. A little bit about something that's related to that test, kind of a belated plug for one of the things we looked at, the vector nature of momentum. A couple practical applications of momentum problems that involve vectors, which I should have mentioned before but I forgot, were accident investigations. Like, for example, the Humboldt Broncos bus crash a couple years ago. A lot of accident investigators, when they're looking at situations like that, they're applying the law of conservation of momentum with vectors, and also a lot of aerodynamics problems. Like, for example, if you have an airplane wing and the flaps are down and the airflow is hitting the flap and being deflected downward a certain angle, well, how much lift is that generating? Believe it or not, that is actually a problem that is solved through the vector nature of momentum. Okay, enough of that. On to what we really want to talk about today. And what we're going to focus on today is power. Okay. Now, when you talk about power, what comes to mind? What's something that's powerful? A lot of people might say, well, a sports car is really powerful because it'll go really fast. Other people, they might say, well, a tractor's really powerful because it'll pull lots. So what does power mean? Does it mean something can go fast? Does it mean that it can pull lots and exert a great big force? Let's take a look at this simple little example here. It's a comparison between a sports car and a tractor. And from this simple little example, we'll get a really good feel for what exactly power means, okay? So here's our sports car, here's our tractor, and you'll notice they both have, if you looked up the specifications for them, they both have 225 horsepower engine in, they both have 225 horsepower engines inside them. So theoretically, these things, they are equally powerful. Oh, okay, let's have a little contest. Let's say both the drivers are going to step on the gas as hard as they can for 1 second, and let's see what happens with each. Well, the sports car, the driver floors it for a second, and the sports car is pretty fast, so it's going to go a relatively long way in that 1 second, let's say 20 meters. It's just a tiny little sports car, right? So it's not going to have to exert a lot of force over the course of that 1 second. Let's say the force generated by the sports car is 1,000 newtons. Okay, what happens when the tractor driver, when they do the same thing? For 1 second, they put the accelerator down, and let's see what's going on there. Well, the tractor, it's going to generate, relatively speaking, a large force for that 1 second, like 5,000 newtons, as you can see, 5 times bigger than the sports car. But the tractor, it's not going to go very fast. Let's face it, it's this big heavy thing. It's pulling this big heavy trailer. The tractor's only going to go in that 1 second 4 meters. Okay, so let's see how much work both of these things did over that 1 meter, or pardon me, over that 1 second time interval. Well, how much work did the sports car do? Work is equal to force times distance. You multiply those two things together, you get 20,000 joules. How about the tractor? same deal. Work is equal to force times distance. You multiply those two things together and you get 20,000 Newton meters or 20,000 joules. Same thing. They both did the same amount of work in the same amount of time. That's because they're equally powerful. Power is how fast you do work. Power is how fast you do work. The sports car and the tractor, they're equally powerful because they did the same amount of work in the same amount of time. They did it different ways, mind you. The sports car did its work by exerting a small force over a big distance. The tractor did its work by exerting a large force over a small distance, but in the end, they did the same amount of work in the same amount of time, so they're equally powerful. So power is, here's the definition, how fast work is done. And we'll take a look at an equation you can use to calculate power. We'll look at the units of power, and we'll also do a couple of example problems. All right, here's a simple little example to start things off. It'll let us figure out an equation for power. It'll also let us figure out the units of power. So it says an electric motor does 100 Newton meters of work in 2 seconds. Find the power generated. Remember, power is how fast work is done. Well, how fast is this thing doing work? If it does 100 Newton meters of work in 2 seconds, well, it's going to do 50 Newton meters of work in 1 second. Of course, how did you get that? Well, you divided. So the power of this thing is 100 divided by 2, which is equal to 50. How about units? This 100 is in Newton meters, so our units are going to have Newton meters on top. This 2 is in seconds, so our units are going to have seconds on the bottom. And there's our answer. The power this thing generates 50 Newton meters per second, which is the same as 50 watts. Okay. So from this little example, we've learned a few different things. We've learned that the equation for power is going to be this. It's going to be just like it says here, the work done over the time some people put a T there, some people put a delta T there to show us a time interval, but regardless, you get the idea. There's the basic equation for power. And the basic unit of power is the watt. Okay, 1 watt, abbreviated with a W, is equal to 1 Newton meter per second, which is of course the same thing as 1 joule per second. Okay. Just to give you some idea about how big a watt is not a lot of power. The average human at rest generates about 100 watts of power. Most humans, like if you're going for a little light jog, they can sustain 300 to 400 watts of power for a few minutes. Top athletes, we're talking Olympic class sprinters or Olympic class cyclists, they can develop upwards of 2,000, maybe even some of them close to 3,000 watts of power. And just out of curiosity, a horsepower is equal to approximately 750 watts. It's actually a little bit less. So that Olympic class cyclist who's generating 2,000 watts of power, or that Olympic sprinter who's generating 2,000 watts of power, that's just under 3 horsepower. When you're just sitting there doing your physics homework and generating 100 watts of power, you know, mostly to keep your body warm and to keep your brain working, that's maybe an eighth of a horsepower. And one last thing we should tell you is that power is a scalar, not a vector. You'll never have to add power on a vector diagram. Makes sense, right? Because power is calculated from work, which is also a scalar. Okay. All right, so now, as I say, you'll never look at a 60 watt light bulb again as long as you live, because now you know exactly what that 60 watts means. That means it's generating 60 joules per second of energy. The light bulb, of course, isn't doing work in the sense that it's lifting something up or dragging something along the floor, but it is creating 60 joules of heat and light energy every second. We'll do another couple examples, a little more involved than this one. All right, here's another example. This one's a little more involved. This is a kind of example, or this is the kind of problem that a mechanical or an industrial engineer might have to work through. Let's see what it says. It says a mine shaft motor must lift its load 100 meters in 1 minute. A lot of mines, they're kind of like assembly lines. You got to get the ore out of the ground up here to the processing equipment, and you got to keep that processing equipment fed. You can't let that processing equipment be running empty. So yeah, as it says, the motor has got to lift its load out of the mine 100 meters in 1 minute to keep that processing plant on the upper level going. The motor's power rating is 20 kilowatts, and most motors, somewhere on the motor, it'll have the power rating stamp there. 20 kilowatts, that's like 20,000 watts. That's about 25 horsepower, like an outboard motor. And here's the question, what is the maximum load this thing can lift? Of course, if you exceed the maximum, it's going to take more than a minute, and the people waiting for it up at the processing plant aren't going to be too happy. If you lift less than the maximum, well, then that processing plant on the upper level isn't running in capacity. So what's the maximum load this thing can lift? So of course, the first thing to do is get a diagram down that involves what's going on here. And here it is. I've pre-drawn it to save time. Here's our motor with a power rating of 20 kilowatts. There's the rope hanging down from it that's pulling the load up from the depths of the mine. And of course, we want to figure out the mass of the maximum load. And of course, just to simplify things, as you probably realize, it's way easier to pull this thing up at a constant velocity than try accelerating it to some tremendous speed. So we'll assume that we're just pulling it up at a constant velocity, and of course the forces acting on this thing are going to be the force of gravity going down and the tension in the rope pulling up. And you might think, well, what does all this down here have to do with the motor up here? Well, take a look where the rope connects to the motor. Remember, tension takes whatever's at the ends and pulls it towards the middle. So if you've got a tension T acting on the mass down here, you're going to have the same tension but opposite direction acting on the motor up here. And then there's Newton's third law, right? For every action force, there is an equal and opposite reaction force. If the rope pulls on the motor with this force, the motor is going to pull on the rope with the same force but opposite in direction. So basically, the force that the motor is exerting, well, it's the same as the tension in the rope. And remember, it pulls this thing up 100 meters in a time of, whoops, not 1 second, in a time of 1 minute. So that's going to be 60 seconds. That's better. Okay, let's see if we can figure out, how much stuff we can jam into our load here. Okay, well, remember, we're given the power of the motor, and power is equal to work divided by time. We know the power of the motor, that's 20 kilowatts, which is 20,000 watts. We know the time involved. The time involved is 1 minute or 60 seconds. How about the work? Okay, well, the work isn't given to us. Okay, but remember, work is equal to force times distance. And here you have an equation. You can solve it for F. And if you solve it for F, the 60 goes across the other side, goes upstairs. The 100 goes across the other side, goes downstairs. If you solve this for F, you get that F is equal to 12,000 newtons. Okay, now remember, we don't really care what F is. What's the maximum load? Like, what's the mass here? Well, I'm pretty sure we can figure that out, right? Remember, this thing is moving at a constant velocity, so that means the force of gravity down is going to be balanced off by the upwards force, F. So we know that the force of gravity is the same as F, which we just calculated. 12,000 newtons. And remember that the force of gravity is the mass times the gravitational field. And we know that's equal to 12,000 newtons. So the mass is what we're trying to figure out, times the gravitational field, which is 10. That's equal to 12,000 newtons. So you just solve this equation. The 10 goes across, the other side goes downstairs, and there's your mass. 1,200 kilograms. That's the maximum load you can put in this thing. If you put in any more, it's going to take longer than 1 minute to pull it up there. If you put it in any less, well, it'll get up there in less than a minute, but it won't be as much as possible. We're going to take a look at one more quick example. All right, here's the last example. It says the motor exerts a 500 Newton force while propelling a boat at a constant 3 meters per second. Find the motor's power. And of course, the first thing you do is get a diagram happening with all the information that you're given. And here it is. Here's our boat and the motor. And you got to remember that the motor pushes backwards on the water with a force of 500 newtons, and the water pushes forward on the boat with a 500 newtons. And even though technically that's the water pushing on the boat, remember, the motor is still responsible for that 500 newtons of force. So of course, that's what we're using. And remember, the boat's going at 3 meters per second, and that's a constant velocity. It's not accelerating. And we want to find the motor's power. Now, if you want to find the motor's power, that means the only force you have to worry about is the force exerted by the motor. You don't have to worry about the drag force with the air, the drag force with the water, or the force of gravity going down and the normal force pushing up. If you're trying to find the motor's power, the only force you have to worry about is the force that the motor is responsible for, and that's this one. Okay, so the motor's power. Well, power is equal to work over time. Okay, work is equal to force times distance. We've got to divide that by time. So we know the force involved, well, that's 500 newtons. How about the distance and the time? It's not given to us really obviously, but it's there. It's wrapped up in the velocity, right? Okay, in a time of 1 second. In a time of 1 second. This thing's going to travel a distance of 3 meters. The time is 1 second, and the distance is going to be 3 meters. And there's your power calculation. Comes out to 1,500 Newton meters per second, or if you like, 1,500 joules per second, or how about 1,500 watts done. And you might notice, okay, you don't really need any extra formulas to do this. The basic power is equal to work divided by time does it, but you might notice that your power is equal to your force times your velocity. Right? The power is 1,500. If you multiply by, if you multiply the force by the velocity, you get 1,500 that way as well. So for people who like formulas, there's another one which is kind of handy. As far as an assignment is concerned on this, I will post one very, very shortly. And of course the solutions will be provided with it. If there's a solution missing from a question or two, those will be posted later, likely tomorrow. Bye for now.